Welcome to part 2. And in this part, we're going to be tackling solutions to the crash consistency problem that we introduced in the first part of this lecture. So let us get into it with the first one being our file system checker. So early file systems took a simple approach to crash consistency. Basically what they did was they decided that we're going to let inconsistencies happen and we're basically just going to fix them later. So, when did they fix them? Well, when rebooting the system. So the classic example of this type of approach is our fcheck or fscheck, which is the file system checker. And it is our Unix tool for finding inconsistencies and repairing them. And what you can see here is, well, what we'll discuss later on is that all it basically checks is the superblock, the free block, the inode states, and the inode links. So it actually doesn't check the data section really. The issue is that such an approach can't fix all problems. And the example that we give here is that the file system looks consistent, but the inodes actually point to garbage data. So there's no way of knowing if your inodes point to garbage data or not. The only real goal is to make sure that the file system metadata is internally consistent, meaning like our bitmaps indicate the correct blocks are allocated and free, and that corresponds to what our inodes say. So let's have a look at the basic summary of what our fscheck does. So in terms of the superblock, fs first checks if the superblock looks reasonable. Okay, and it mostly does some sanity checks, such as making sure the file system size is greater than the number of blocks that have been allocated. And usually the goal of these sanity checks is to first find like a suspect or corrupted superblock. And in this case, so the goal is to find a suspect superblock. And in this case, the system may decide to use an alternate copy of the superblock. And if you remember, well, if we're utilizing our FFS, there is multiple superblocks across all groups, so you can use any one of those. The next thing that our file system checker does is it scans our inodes, our indirect blocks, our double indirect blocks, that should be, to build an understanding of which blocks are currently allocated within the file system. So it uses this knowledge to produce a correct version of the allocation bitmaps. Thus, if there are any inconsistencies between the bitmaps and the inodes, it is resolved by trusting the information within the inodes. So if an inode points to a specific block, well then, if the inode points to a specific block and then the bitmap says that that is unallocated, well, we're going to trust that the inodes are correct and and update our bitmap to reflect that. And the same type of check is performed for all the inodes, making sure that all the inodes that look like they are in use are marked as such in our inodes bitmap. Okay, then the next one we need to look at is our inode states. So each inode is checked for corruption and other problems. For example, fscheck makes sure that each allocated inode has a valid type field. So e.g. like a regular file, a directory, a symbolic link, stuff like that. And if there are any problems within the inode fields that are not easily fixed, the inode is considered suspect and cleared by fscheck. So cleared like freed. And then the inode bitmap is updated correspondingly. So if there's an issue that cannot be easily fixed, the inode is considered suspect and cleared. Now the fourth one that we need to consider is our inode links. So fscheck also verifies the link count, the link counts of each allocated inode. As you may recall, the link count indicates the number of directories that contain a reference, like that link, to a particular file. Now, to verify the link count, FSCheck scans through the entire directory tree, starting at the root, and it builds up its own links, or it counts the links in its own mind for every file and directory in that file system. And if there is a mismatch between the newly calculated counts and that found within the inode, well, obviously there's an issue, right? So corrective action must be taken, and it's usually done by fixing the count within the inode. So we usually fix the count within the inode itself. Now, if an allocated inode is discovered, but no directory refers to it, it is moved to what we call the lost and found directory. And in this directory, you'll basically find recovered bits and pieces of corrupted files. So it's like a trash bin, basically, of corrupted files that may or may not be recovered, depending on other tools and stuff like that. Now, FSCheck also handles duplicate pointers. Now, these are cases where two different inodes refer to the same block. Now, if one inode is obviously bad, it may be cleared. Alternatively, the pointer to block could be copied, thus giving each inode its own copy as desired. So they could be copied and stored in like two separate blocks, and then you would just have two inodes pointing to two separate blocks with separate data, basically, even though the data is the same. In terms of bad blocks, a check for bad block pointers is also performed while scanning through the list of all pointers within like an inode. A pointer is considered bad if it obviously points to something outside of a valid range. Example here is that if it has an address that refers to a block greater than the partition size, and in this case, FSCheck can't do anything too intelligent. It just removes or clears the pointer from the inode or the indirect block. So in other words, it just removes the pointer. As you can see, FSCheck does quite a bit. In terms of directory checks, FSCheck doesn't actually understand the contents of user files. However, directories hold specifically formatted information created by the file system itself. Thus, FSCheck performs additional integrity checks on the contents of each directory. The example of this is that it makes sure that like our dot, which is the current directory, and our parent directory are like the first entries, for example, that each inode referred to in a directory. It also checks that each inode referred to in a directory entry is actually allocated. And lastly, it ensures that no directory is linked to more than once in the entire hierarchy. So you can't get like that circular, circular directory setup that we talked about last week. So as you can see, like there's a lot of things that it does. So building a working FSCheck requires like some intricate knowledge of the file system itself, like the underlying implementation. However, the file system checker has a bigger and more fundamental problem, and that is the fact that it is too slow, because it requires scanning the entire disk, and this may take many minutes or hours. And the performance of FSCheck became prohibitive or like really bad as our disks grew in capacity, as well as a result of like RAIDs, which is like that redundant array of independent disks, which is a way of like combining multiple separate disks into a single like logical disk. And because the disk size got a lot bigger, obviously the time taken to scan increased as well. At a higher level, so not just like the fundamental speed level here, at a high level, the basic premise of FSCheck is a little bit irrational as well, because it is incredibly expensive to scan the entire disk. It works, but it is wasteful. And because of this, researchers started looking for some other solutions. And the solution that they found or they came up with was thanks to database management systems, to be honest, and that was called journaling. Now, this is probably the most popular solution to the consistent update problem. And like I said, it's an idea stolen from databases. The idea is known as the write-ahead logging and was invented to address exactly the type of problem that we were discussing. And we call it journaling because this is more for historical reasons. That's what it was referred to in databases. But yeah. So how does journaling actually work? Well, the idea is relatively straightforward. And how it works is that when updating the disk, before actually performing those writes to those structures, let's just write down a little note describing what I'm going to do. So this note will indicate the exact steps that I'm going to take and what I'm going to write and where. And I'm just going to store that first in case of a crash. So writing this note is the write ahead part. And we write it to what we call a log. So the structure that we write is called a log. And by writing the note to the disk, you're guaranteeing that if a crash takes place during the update of the structures that you're updating, you can just go back and you can look at that note. And you see what you wanted to do, and then you can try do that again. So thus, you'll know exactly what to fix after a crash instead of having to scan the entire disk, because you've left these notes. And if you see, okay, this is what I wanted to do, but it wasn't done, there's obviously an inconsistency there that you can directly solve. So we're going to describe how journaling is incorporated into a specific Linux file system, this EX3. Because EX2, which is kind of what we talked about last week, didn't actually have the capability of utilizing journaling. That wasn't around back then. But EX3 had it as a feature. So the new key structure is the journal itself, which occupies some small amount of space within the partition. So if you remember, this is what we've seen before, right? We had our super block, and then maybe the bitmaps are these ones, and the inode, this one, data blocks, etc. Now the only thing that's different is, well, one of the blocks is now our journal itself. Okay. So that's the only difference really, but what's inside the journal is important, obviously. So say we have that canonical update again. So it's that update with those 3 steps. So say we wish to update our inode, our bitmap, and that data block DB from that original example. Before writing them to their final disk locations, all we're going to do now is going to write them to a log. We're going to first write this process to a log. So it's like a temporary storage, basically, or temporary writes. And inside this log, it's going to look like this. So we're going to have this TXB and then the 3 things that we wanted to write and TXE. So what is TXB? Well, it's an indicator of the transaction begin, or where a transaction begins, okay? And it contains some kind of transaction identifier, all right? Because we're gonna have multiple different things in our journal, multiple transactions, we need an identifier, and that's stored in this TXB. The middle 3 just contain the exact contents of the blocks like I mentioned, and this is known as physical logging. And then lastly, TXE, well, obviously if we have a begin, we need to have an end. And it indicates or it marks the end of a transaction, and also contains the same TID value as our begin block. So we can use these to basically encapsulate our 3 writes, or to surround our 3 writes. So once this transaction is safely on the disk, we're ready to overwrite the old structures in the file systems, and this is a process called checkpointing. So once we've stored this in our journal, we're able to do the actual transaction safely. So what that means is thus, to checkpoint the file system is to bring it up to date with the pending updates in the journal. So here we actually issue the rights to our inode, our bitmap, as well as that new data block. And if these rights complete successfully, we have successfully checkpointed the file system and we are basically done. So the first step is to journal and then to checkpoint. And that's what you can see here. So our initial sequence now of options with this data journaling is to journal write. So write the transactions that we want to perform into the journal. Okay. And then once that is successful, then we can actually do the writes. So how does this affect, well, when crashes occur? So in our example, we would write our TXB, our IV2, BV2, DB, and TXE. Okay, so that's 5 transactions. And when these writes complete, we would then complete the updates by checkpointing the IV2, the BV2, and the DB to their final disk locations. So once this journaling step was finished, we could then checkpoint. Okay. Now, what ends up happening is that this is quite a slow process to complete. Because you have to wait for each of them to complete if we had to do the transactions each one at a time. Okay, but things get a little trickier when a crash occurs during the writes to the journal. All right, we're trying to solve crashes when we write into the data to the actual locations on disk, but there's nothing to stop it from crashing when we're trying to write to the journal. So one simple way would be able to, so like I said, this is a simple way to do it, like perform each transaction one at a time, but it is slow and it can lead to inconsistencies if crashes occur during this time. Ideally, we would like to issue all 5 block writes at once, which is like this option number 2, as this would turn 5 writes into like a single sequential write, which is a lot faster. However, this is also unsafe because given such a big write, the disk may internally perform some scheduling and complete small pieces of the big write in any order. So again, this write could occur in any order, which is also an issue in terms of crash consistency. So either way, we've got kind of a little bit of an issue here. So how do we get around this problem of maybe a crash occurring while we're trying to do that journaling step? Okay, so why is this like internal disk scheduling an issue in terms of if we were able to write all the blocks or all the transactions at the same time? Well, you could get an example where the disk internally may perform TXB, IV2, BV2, and TXE, which would be the end, and only later write to DB. Well, in this case, all transactions look like they are valid, as it has a begin and an end with a matching sequence of numbers. So these begins and ends would match. But the file system would not be able to look at the 4th block and know it is wrong, right? This database block here, or this data block here. Thus, if the system would reboot and run some sort of recovery now, at this stage, it will replay this transaction, okay? It would replay this transaction here and ignorantly copy the contents of this now garbage block to the location where DB is supposed to live. Okay, so this is obviously bad for arbitrary user data in a file, as it is much worse though if it happens for like a critical piece of the file system, such as the super block. So say we were updating the super block over here, all right? And if this would then lead to this condition here where we would have like garbage data in the super block, the system or the file system might become unmountable. So that's obviously a big issue if we have this interleaving of journal transaction writes here that could occur due to disk loses like power, for example, or like the interleaving of the scheduling. So to avoid this problem, the file system issues a transactional write in 2 steps. So instead of doing it all at once, and instead of doing it all individually, it does it in 2 steps. Okay. So first it writes all the blocks, all the blocks except the TXE block to the journal, which makes sense, right? The TXE is telling us that we ended, so this should only be written like when we've properly finished this task. So when these writes are complete, then the file system issues the writes to the TXE. Okay, so the file system will then issue the writes to the TXE, thus leaving the journal in its final safe state. Okay, and this is a little additional thing. An important aspect of this process is the atomicity guarantee provided by the disk. So the physical, physics of the disk and how the writing process occurs provides atomicity when we're performing the writes in this type of fashion here. So now how does our transaction process look like, or our writing to disk process look like? Well, first we do our journal write like we did before. Okay, and we write the contents of the transaction to the log. Okay, that was like our bitmap, our inodes, and our data. Then we do a journal commit, which is we write the transaction commit block, and we perform the journal writing where we do the first 4 blocks, and then we do after that succeeds, then we do the exit or the end. And then we checkpoint, so we write the contents of the updates to their actual physical disk locations. Cool. So that was data journaling and how to actually write data using this journaling approach. An additional component to look at is recovery. So now with this setup, if a crash happens before the transaction is written to the log, our pending update is skipped. Okay, so if we don't even get to write stuff to the log and get that log step finished, well then we'll just skip this update. If the crash happens after the transactions is written to the log, so we have that nice begin, the blocks, the end, well, but there's a crash just before the checkpoint, what we do is we recover the updates by scanning the log, looking for the transactions that have been committed to disk, and we basically replay all the other transactions. So if I go back to this diagram quick, so if this is currently in our log, and that's all the journaling steps done, and then we're going to commit, but a crash occurs, what we do is we then just replay this. Okay, so we replay this and then we commit. Then we do the checkpointing afterwards. But that brings us to maybe another issue is, well, if we have multiple transactions pending, how big can our journal actually get? What happens when our journal gets too big as well? Well, the log is of a finite size, right? And we can have multiple logs sitting in our journal. And 2 problems arise when the log becomes full. Firstly, the larger the log, the longer the recovery will take, as you have to replay multiple transactions. That's a little bit simpler, but less critical of a problem. The issue is that no further transactions can be committed to the disk. So until these transactions are processed, you can't actually make any changes, and that's obviously less than useful. So to address these problems of our journal size being limited, journaling file systems treat the journal as a circular data structure. So if you think of like a circular array or a circular list, you end up reusing it over and over, and that is why the journal is referred to as a circular log. Now, to do so, the file system makes action sometime after a checkpoint. To do so, the file system must take action sometime after a checkpoint. Specifically, once a transaction has been checkpointed, the file system should free that space. So once it's been once you add the transaction to the journal and then it is actually being checkpointed, it is no longer useful to remain in the journal, right? It's been processed, so it should be freed at that point. So how this looks is that our journal has like a little super block within itself, okay? And this block tells us, or it marks the oldest and newest transactions in the log. And these are the oldest and newest non-checkpointed transactions, okay? All other, like our checkpointed transactions, are freed, and all other space is freed. So the journaling system records which transactions have not been checkpointed, and that is how this like circular structure works, by having it pointed to the oldest, the oldest would be here, and then the newest would be here, and keeps track of that. So there is still a slight problem, and that is because we have to write every data block to the disk twice, right? When we commit it to the log, okay, you can't see it there. Sorry, I'm going back. Just want to describe this. So when we commit it to the log, we're actually writing that data block to the journal itself as well, along with our inodes and our bitmap, but it's there. So this is still a problem because we're basically writing our data twice, every single time. The first to commit to the log or the journal file, and the second when we checkpoint or actually write it to an on-disk location. Now this is slightly inefficient. So people have tried a few different ways or things in order to speed up this performance. And the one way is that they came up with a simpler form of journaling, and that is called ordered journaling, or simply metadata journaling. And in this approach, it's pretty simple. All you do is you don't write the data to the journal, or the data component to the journal. So now our transaction would look something like this. And this is what the information would be in the journal. So I'll begin, our inode version 2 from that same example, our bitmap version 2 from that same example, and the end. The data block, which was db, which was previously written to the log, would instead be written to the file straight away, written to the on-disk structure straight away. This modification does raise an interesting question, and that is, well, if we're not writing our data in our journal, well, when should we actually write data blocks to the disk? So there's two different approaches, right? The first being, let's write data to the disk after the transaction. Unfortunately, this approach has a problem, as that file system inconsistencies might arise, because our inode may end up pointing to garbage data. Why? Because it could be updated at some point. And I'll show you an example of this on the next slide. The second is that, well, why not just write data to the disk before the transaction? What this does, thankfully, is it ensures no data-related problems. There might be other inconsistencies, but there's no data-related problems. You wouldn't have a case where an inode points to garbage data, which is kind of what we want. Okay, so let's look at a case which demonstrates the issues here, all right? As well as an additional issue and that being that some metadata transactions should not be replayed. So some transactions shouldn't actually be replayed. An example of that is, well, directory foo is updated. So here we can see we're updating the directory foo, okay? After which directory foo is deleted and block 1000 is freed for reuse. Now that doesn't require any transactions with the journal, okay, but it does occur. And then after that, once again, a user creates a file called foobar, which uses this block 1000 data for data. So there's a file now that should be starting at this address. Okay, so our journal kind of looks like this now. Okay, where we the first step here is basically updating our foo with some update. And over here, we're updating our inode or foobar to point to that location of the file. Okay, and those are our two transactions. Now, what if now if you assume that a crash occurs and all of this information is still in the log? Well, during the replay, the recovery process replays everything in the log, right? Including the writes of the directory data in block 1. So including this update, right? But you remember this was freed, so this would have been empty. But at this point, it wasn't, and it had some data here with this updated data. So it's going to redo that update process. And now what ends up happening is that the replay overwrites the user data of the current file foobar, because we're updating this data location, right? And it's updating foobar with some old directory contents, and that's obviously an issue. So what the solution is that in terms of our Linux file system that we've been working with today, is that it adds a new type of record to the journal known as a revoke record. And when replaying the journal, the system first scans for such revoke records, and any such revoked data is never replayed, or any such revoked data is never played. So for this one, there would have been a revoke for this, and it would never be replayed. Cool. So those are our two journaling journaling types. We have data journaling and metadata journaling. Now, before ending our discussion on journaling, we're just going to summarize the protocols we have discussed with the timelines depicting each of them. And that's what you can see here, a timeline. Now, this is an example of the data journaling protocol that writes, where writes of the transaction block begin at TXB. So that's here. And the contents of the transactions can logically be issued at the same time. So that would be these two components here, the metadata and data components. And these can be completed in any order. It doesn't really matter. However, what is important is that the writes to the transaction end, or the TXE, okay, must not be issued until the previous writes complete. Okay, so until these are completed, these TXB, metadata, data are completed, the TXE cannot be issued to be written yet. And similarly, the checkpointing writes to the data and the metadata blocks cannot be issued until this TXE is completed. So that's why you can see these come after, like after these dashed lines. And once again, these can be issued and completed in any order as well. So that's how the data journaling works. And if you remember earlier, it follows from there. You remember we do these three first, and then this one, and then the checkpointing, and that's that flow. Now, a similar timeline is also here shown for metadata journaling. And here you can note that the data writes can logically be issued at the same time. Okay, it can be issued whenever here, at the same time as the writes to the transaction begin and the contents of the journal. However, it must be issued and completed before the transaction end has been issued. So before this guy is issued, this guy has to be completed. And there's a final note that the time of completion, which is marked for like each write in the timeline, is arbitrary. Okay, it doesn't really matter. Well, the times that these take are arbitrary. And in the real file system, the completion time is obviously determined by the actual, the actual system. So yeah, that is metadata journaling. And once again, the key parts here is that we don't have a data component here. It's just our metadata stuff. And the data component happens over here. And it's just written to the file system straight away. Whereas over here, we write to the journal. We write the data to the journal. And we write the data to the file system as well. So it's that double entry. Okay, so that is it for basically what we're going to be covering in this course, as well as for this chapter. Now, I know it's been somewhat of an unusual course. I mean, I haven't met or seen any of you, and yet we've come along through, I don't know, like 14 or so weeks. So I just want to say thank you guys, whoever's been watching the videos, and I hope it's all been at a relatively decent standard. I know some weeks have been better than others. But once again, yeah, thank you to everyone, And I've enjoyed making the lectures and the videos and stuff like that. It's been interesting. I've somewhat been learning along the way with you guys at the same time. And I just want to wish you guys good luck for all your tests, including operating systems, obviously. And good luck for the rest of the year. All right. Thank you guys, and cheers.